Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 26. Today we will begin to look at another type of bipolar amplifier topology, which we call the common base stage. And this has some interesting properties, some properties that are different from the common emitter stage, and we will see why we might choose one over the other. Now, before we go there, I would like to just take a step back and look at what we have learned in the past few lectures in terms of amplifier design and the properties of the common emitter stage. So here's our Circuitpedia board. As you can see here, let me get the lighting right. So this is where we are. We have investigated a common emitter stage in its basic form. We saw that if it's a simple stage without degeneration, then the input impedance is R pi. That's what we measure between the base and ground using small signal analysis. The output impedance is RC in parallel with RO, again measured from here with respect to ground if we place this in a black box. And the voltage gain from the input to the output is given by minus GM RC, or RC in parallel with RO if we want to include that. So maybe I'll include that here just for completeness. Okay, then we went ahead and added a degeneration resistor because our hope was that it would reduce the sensitivity of the circuit's parameters, such as the bias current or the gain, to various factors. For example, temperature or process or even the signal level. And we saw that the overall voltage gain from the input to the output now assumes this form. And in particular, we see that 1 over GM is not added to RE. So if RE is comparable to or quite greater than 1 over GM, then the variations in 1 over GM as a result of temperature and process and signal amplitude will be lesser in the overall picture than what we had here. Here, if IC changes by 10%, the gain changes by 10%, whereas that is not the case here. We also saw that the degeneration alters the input impedance. It raises the input impedance significantly by an additional term of beta plus 1 times RE. And then the output impedance was still RC, provided that we have assumed a negligible early effect for actually all of these calculations. And then we added some bias components. We wanted to bias the base, so we added a resistive divider here to provide the bias for the base. And we saw again that degeneration was helpful in terms of bias stabilization. So these are the things that we have learned about one particular topology. Now we're going to go to another topology. The next topology is somewhat different, but with the foundation that we have produced here, we should be able to learn the other topology much more easily. So let's go and take a look. All right, so today we're going to talk about what we call the common base stage and understand some of its basic properties, and then see how we can bias it, just the way we bias the common emitter stage. So here's the basic common base stage. We have a transistor. This time I will draw the transistor pointing this way, like so. Not a big deal. You can always draw it that way too. It's a little easier to draw it this way for common base. But again, that's not something that everyone agrees on. So we have a resistor from the collector to VCC as usual. But this time, the signal, the input signal, does not go to the base, it goes to the emitter. So the signal comes in here, we can call it V in, and goes out of the collector. We call this V out. What do we do with the base? Well, the base needs some sort of bias, because after all, this junction has to be forward biased. So we add a battery from here to ground for now, and later on we'll have to see what to do with it. So we'll call this V0. So to identify a common base stage, we must ensure that the input is applied to the base, to the emitter, applied to the emitter right here, and the output is sensed at the collector. So output sensed or taken at collector. So if you have some complicated circuit diagram with lots of things going on, the way we would tell whether this particular stage is a common base stage or not is by looking at this particular input, right? The input has to go to the emitter, not to the base. Okay, so this is what we call the basic common base stage. And it has some interesting properties, as we will see soon. Well, our general objective with analyzing these types of circuits is to find their voltage gain, their input impedance, and their output impedance, as we did with the common emitter stage. So that's what we should embark upon and try to analyze. All right, so what we are looking for are AV, R in, and R out. Okay, so let's first ask about the voltage gain. This topology is not something that I have analyzed before, so I cannot use the previous equations for the voltage gain of the stage. That means I have to draw the small signal equivalent circuit and analyze it just the way we did for the common emitter stage. So let's draw the small signal model, starting with the transistor itself. So how do we draw that? In fact, this time I will draw it like so. I need to have enough room for my drawing. We start with the emitter. So we know that in the emitter we have something like this. And then between base and emitter we have R pi. And then we have V pi across it. This is GM V pi. And in this analysis, I'm assuming the early voltage is infinite, so we don't have to worry about the early effect. Okay, so you have to turn this around in your mind. We are used to seeing the small signal model of the transistor like so. Base to emitter has R pi, collector to emitter has this and that, right? Now we have to switch this over because our base is located on the right-hand side. It just happens that way, right? So that's what we'll do. We'll take the base on this side, the collector on this side. Okay, what happens to the base? The base is connected by a constant voltage source to ground. So because this voltage source does not have change with time, it will be set to 0. A 0 means a short circuit, so that goes to ground. The collector goes to a resistor. So here's our resistor RC. And then the top terminal goes to a battery that goes to ground. So again, the top terminal is at AC ground. So that is also at ground. All right, and the input is here. This is the small signal input, and the output is here. You can see at the collector. I can draw it this way, I can draw it this way, it doesn't matter, so this is the output. I hope you recognize the critical distinction between this symbol and this symbol. This symbol means we have a voltage source applied between here and ground. Because we are lazy, we just don't draw it. But this is driven by a voltage source. Whereas this one says we are just measuring the voltage. We're not applying anything. So it's as if you had a voltmeter, you put it over there, you try to measure the voltage. So these two, even though look the same, are very different symbols. Okay, all right, so now we just need to find V out over V in as the voltage gain. And as usual, we will try to eliminate V pi. So in fact, to make things a little easier to understand, let me erase this and draw a voltage source explicitly. That might be a little easier in this case. So V in. All right. Well, it just happens in this particular circuit that V pi is related to V in very directly. Let's trace and see. The bottom terminal of R pi goes to the top of V in. The top terminal of R pi goes to the bottom of V in. So the voltage across R pi and V in are related. Are related by a factor of -1, because V pi has its positive end over here, whereas V in has its negative end over here. So we just have V pi equals minus V in. So that was easy. Now that that's the case, we can readily calculate everything. What do? Well, we will probably want to write a KCL at this node, and knowing that the current flowing through RC is equal to GMV pi, right? That's what KCL tells us. Okay, how much is the voltage at the output? Well, V out is equal to RC times the current through it. Which way? The current has to go upward. It has to go from here to ground, upward. How much is the current going upward? Well, it's equal to minus GMV pi. So this current is equal to minus GMV pi. Again, notice that I try to draw everything on the circuit. I don't try to introduce new variables, call this I1 or IC or IX or something. I just keep it as minus GMV pi. Okay, so if this current is minus GMV pi, and I multiply it by RC, I find V out. So V out is equal to minus GMV pi times RC. And because we have V pi, we have minus GM times minus V in times RC, which says AV, the voltage gain of the common base stage, is equal to GM times RC. That's pretty cool. So the voltage gain of a common base stage is similar to that of a common emitter stage, except that it doesn't have the negative sign in front of GM. All right, so that's the only difference. In other words, the gain of a common base stage is positive. It doesn't flip the signal over, whereas the gain of a common emitter stage is negative, so it flips the signal over. Okay, that was easy. So here's the voltage gain of the stage. How about the input impedance? The input impedance is defined as the current, the apply voltage here, measure the current, divide this voltage by that current. All, of course, in small signal regime. And that would be the input impedance, assuming that we set all independent sources in the circuit to 0. Now, you could go ahead and draw this small signal model and set the independent sources to 0 and apply a voltage source and measure the current. But we have it here really, right? So because we're lazy, we won't draw the circuit again. We'll just try to do it over here. But it's good to change our color, our pen color. So let's go to red and see. Okay, so the input impedance is defined as the small signal voltage that we have applied to the input divided by the current that would result from it. Now, ordinarily, In previous calculations, we would call this Vx and this Ix. This time we just call it V in and I in, but it's the same thing. So can I find I in here? And again, I in has to be in terms of RC, RPi, and other circuit parameters, but not in terms of Vpi. Vpi has to be eliminated. Okay, well, I in can be obtained if I write a KCL at this node. So let's do that. At this node, I in is going in, GM Vpi is going in, and Vpi over Rpi is going in. That current is Vpi over Rpi. So we just write the KCL here. So we're calculating R in now, and we say I in is going in, plus GM Vpi, that's also going in, plus Vpi over Rpi is 0. Now we have Vpi as minus V in, so that tells us that I in is equal to, let's take these to the other side, factor Vpi and replace it with minus V in. So that tells us V in times 1 over GM plus Rpi. Okay, so that says that I can also write this as V in 1 plus GM Rpi divided by GM, right? And how much is GM Rpi? GM Rpi is beta. And beta is much greater than 1. So I can write this as approximately equal to V in times, if GM Rpi is much greater than 1, I can knock out to this 1. And then I end up with GM Rpi over GM. So that means that, let's see, did I make a mistake here? Beta plus 1. Okay, let's see, we have a mistake here. V in, I in is equal to plus GM Vpi plus Vpi over Rpi equals 0. So we have 1 over GM. Oh, I'm sorry, this should be, I switched these around a little, so let me go back and correct these expressions here. Okay, so let's go back. All right, so we have V in, and then we have GM plus 1 over Rpi. I had flipped these over, so 1 over Rpi. Okay, so that gives us V in times GM Rpi plus 1 over Rpi, and that's beta plus 1, approximately equal to beta. So we have V in times, if I neglect this 1 here, because GM Rpi is much greater than 1, I can cross out Rpi with Rpi, and that just ends up being equal to GM. So the final result is very simple. It says R in is equal to 1 over GM, because V in over I in is 1 over GM. So that is the input impedance of a common base stage. Is that a relatively large number or a relatively small number? Well, if the collector current is, for example, 1 milliamp, then 1 over GM is 26 ohms. So it's not a very large number. It's a relatively small number. By contrast, if you remember, the input impedance of a common emitter stage is Rpi, what we had here, and Rpi was beta times 1 over GM. So it's 100 times bigger. So what we see looking into the input of this common base stage is about 100 times, or beta times, smaller than what you would have looking into the base of a common emitter stage. So the input impedance is substantially lower than that of a common emitter stage. Now that might cause some confusion. Originally, when I was trying to find the input impedance, I said the input impedance is troublesome because when we connect the microphone to the common emitter stage, we have some attenuation if the microphone is not an ideal voltage source. So then, is the circuit any good if its input impedance is so low? Previously, I claimed that the input impedance must be as large as possible so as not to load the microphone, not to create attenuation. But here, I have a low impedance. Well, the circuit has its own applications. Maybe not for a microphone with the characteristics that we considered before, but there are some other cases where the circuit could be useful. I'll give you an example. So in fact, for that example, I'll take you back to many, many lectures ago, and I remind you what happened to our Bluetooth receiver. So we said that a wave arrives at the antenna generates an electrical signal here, and then that signal goes to a low noise amplifier. Because we need to amplify the signal is very small. Now, right here, at this interface between the antenna and the LNA, something must be going on. So let's talk about that. All right, so let's talk about the antenna LNA interface. So here's our antenna, and here's our LNA. Now these are all high frequency signals, the gigahertz or 2 gigahertz or 5 gigahertz, etc. Now you might remember from your electromagnetics courses that if we connect an antenna to another circuit, at this point we have to have impedance matching. So right here we need to have impedance matching, and by that we mean the impedance the input impedance of the LNA must be the conjugate match of the impedance of the antenna. In a simple language, if the antenna has an impedance of 50 ohms, the input resistance of the LNA also has to be 50 ohms. That's what we call impedance matching. Now, we won't go through the reasons for impedance matching, but that's necessary in a case like this. Now, because antennas are typically designed with a relatively low impedance, about 50 ohms, then we would like to have an LNA whose input impedance is 50 ohms. And this would be a good candidate, right? 50 ohms can be obtained if we pick the collector current, the bias current, to be maybe half a milliamp, right? 52 ohms would get us from here. So there are some applications for the common base stage where the low input impedance is useful. Okay, so in this case we are saying that the input impedance of the LNA is equal to the impedance of the antenna. And if the antenna is designed for 50 ohms, then the input impedance of the LNA should be also 50 ohms, and that would call for a common base topology. All right, so that's on the use of the common base topology. Very good. Let's calculate the output impedance as well. So for R out, what do? Well, we can draw the signal circuit again. So remember, for output impedance calculation, which is the same as Thevenin impedance calculation, we set all the independent sources to 0, including the input voltage source. So this input voltage source must be set to 0. Then I put this whole thing in a black box, take its output from here, and then apply a voltage from outside and measure the resistance. So let me draw the small signal model because that might be easier to see. All right, so this time I will try to confuse you. I will draw the small signal model in the normal way, the way we did it before, meaning the base will be on the left and the collector will be on the right. Okay, so here's R pi, V pi, GM V pi. All right, I'm drawing the small signal model of this circuit here. It's okay, I can draw it this way, I can draw it that way. It's just all a matter of drawing. All right, so the base goes to AC ground. So that goes to ground, no worry there. The emitter is coming from an ideal voltage source. And in our output impedance calculation, we must set this independent source to 0. So we'll take this and connect it to ground. Okay, so this represents the fact that V in must be set to 0. That's what Thevenin tells us if we want to calculate the Thevenin resistance. Okay, then from the collector we have a resistor to VCC, which again becomes ground. This is the output node, right? And Thevenin says, put all of this in one giant box, connect the voltage source from outside, which we ordinarily call Vx, and measure Ix. Vx over Ix is the output impedance of the common base stage. Okay. Now, if you look at this very carefully, you will soon realize that we don't actually need to do any calculations. Why? Well, because of the following. Let's go ahead back to our common emitter stage and try to draw the small signal model of this circuit, again for the purpose of finding the output impedance. All right, let's do that. So I will draw the small signal model of the common emitter stage again. So remember, we have the transistor, so it's like this. It's driven by a voltage source, an ideal voltage source, the input V in, so R pi here, GM V pi here. Okay, so I'm going to refresh your memory if I can juxtapose these two. So the emitter goes to ground, emitter goes to ground. The input is driven by a voltage source, but for output impedance calculations, I have to short that voltage source, so that goes to ground. Then we have RC to VCC. We have RC to VCC. VCC is AC ground. So VCC is AC ground. And again, the output is here. So we put this in a giant box and we calculate the output impedance by applying a voltage source and measuring the current. So now if you eyeball these two circuits, what do we see? They're the same. And this is because when we are calculating the output impedance of the circuit, we don't know where the input is. I repeat, when we are calculating the output impedance of a circuit, we don't know where the input is. Why? Because the input was set to 0. Whatever it is, voltage or current was set to 0. We have no idea where it is. Is the input connected between base and ground, common emitter stage, or is it connected between emitter and ground, common base stage? We don't know because we set it to 0. That's why these two circuits look identical. That's why the output impedance of this circuit and the output impedance of this circuit are identical. So for the common base stage, we also have R out equals RC. So we don't need to do any extra calculations. Again, remember that for all these calculations, I'm assuming that the early voltage is infinite, right? So only in this case can we make all these claims and find these numbers so easily. All right, so we have found the voltage gain, the input impedance, and the output impedance of the common base stage. These are the basic properties. We're comfortable with them, and so now we can move on. What we have seen so far are two differences between the common emitter stage and the common base stage. In the common emitter stage, we saw that there was a negative gain here, whereas for the common base stage, we have a positive gain here. And the other one is that the input impedance of the common emitter stage is R pi, somewhat of a high number, whereas for the common base stage is 1 over GM, quite a low number. So those are the two primary differences between these topologies. All right. So let's take a look here. So I wanted to pose a question to you. It's a point of curiosity, but it's good to understand. So here's a question. Why doesn't the CB stage invert? Meaning, why is the gain of the common base stage positive, not negative? So, of course, the equations tell us that's true, but can we have some intuition as to why that happens? So let's do this. Let's take a common base stage, and let's put a battery for now here to make sure that the base has the right amount of voltage on it. And let's assume everything is biased up. I'm not showing the biasing network right now. Assume everything is good. The transistor has the right bias current, GM, VBE, collector base is good, so everything is good. And I come along and I change the input voltage by some amount, delta V. So the input voltage starts at a lower value and goes to a higher value, maybe by 10 millivolts, for example. Okay. So what happens at the output? If this is RC, what goes on here? Okay, so we have to ask ourselves, when the emitter voltage goes from a low value to a high value, what happens to the collector current? So here's the situation. The base voltage is fixed by a battery. The emitter voltage was here, now it goes over here. So what happens to the base emitter voltage? Base is here, fixed. Emitter is down here, and now emitter goes up. So the base emitter voltage difference decreases, right? Base is constant, emitter goes up, the base emitter voltage decreases. So as a result of this delta V, we see that the base emitter voltage decreases. It's an NPN device, so when the base emitter voltage decreases, the collector current decreases. So IC decreases. Now, if the current that we are drawing from this resistor decreases, what happens to this voltage? This voltage goes up. This is something that we repeatedly see in our study of electronic circuits. And this is something you really have to be comfortable with. If this current decreases, this voltage goes up. Get this right once and for all in your mind. And the way to think about it is that the top terminal is held at a constant potential, and we're drawing a current. So when we draw a current, this bottom terminal is lower. And as the current decreases, the bottom terminal goes up. Or you can just write this as VCC minus RCIC. And now you can see that if IC is less, this voltage is higher. So we see that in response to a positive change at the emitter, the collector voltage also goes up. Okay? Because the current through the transistor has decreased. This is in contrast to the common emitter stage. in the common emitter stage, when the input, which was going to the base, increased, the base emitter voltage also increased, the collector current increased, the output voltage dropped. But here, when this goes up, the current decreases, this voltage goes up, and we have no inversion in the circuit. All right. In the next part, I will give you a quiz for the day. It's an interesting quiz. So let's go and add a page here. Look at a little circuit that I have cooked up here. All right, so here's the circuit that we have. We have a simple common emitter stage, V in, RC1. And then this goes to a common base stage, RC2. These are actually connected together. They're connected to what we call VCC. Let's connect this to a battery for now. Call it V0. And the output is here with respect to ground, V out. We call this Q1, Q2. If you want to call this node X. So we see that we have a cascade of amplifiers. We have a common emitter stage followed by a common base stage. Remember that a long time ago we studied the cascaded amplifiers where we had only one common emitter stage followed by another common emitter stage. This time I have mixed the two. So I have some of this, some of that. And our objective is to find the voltage gain defined as V out over V in, meaning the voltage gain from here all the way to here. I will give you 90 seconds. All right, so what did you get for the overall voltage gain? Well, remember for cascaded stages, what we do is we say V out over V in is equal to Vx over V in times V out over Vx. And we find each of these individually, and then we will multiply. So V out over V in is equal to Vx. Sorry, these are all small signal quantities. So Vx over V in times V out over Vx. Okay, so let's go ahead and find Vx over V in. Vx over V in. That is the voltage gain of this common emitter stage. The voltage gain of a common emitter stage without degeneration was what? Was minus Gm times, if you remember, minus Gm times the total resistance that we see between the collector and AC ground. Now, if we have early effect, we have to include that. Otherwise, it's just RC in this case, right? But what we remember from verbalizing this equation was that we have to find the total resistance that is connected, that is tied between the collector and AC ground. So here, so again we're assuming the early voltage is infinite for simplicity. If I sit here at the collector of Q1, I see RC1 to AC ground. VCC, this top rail, is always grounded because it doesn't change with time. Okay, but is that the only resistance that we see at the collector of Q1? Well, if we go this way, this is not an open circuit. It goes into something. It goes into the emitter of a common base stage. So if I sit here and look to the right, what do I see? Remember from the previous page that looking into the input of a common base stage, you see approximately 1 over Gm of the transistor. So the total resistance that's tied between the collector of Q1 and AC ground consists of RC1 in parallel with 1 over Gm1. Why parallel? Well, because when we calculated 1 over Gm2, when we calculated 1 over Gm2, how did we find it? We found it with respect to ground, right? If you go back to the previous page, you can see that this is how we measure the input impedance. We measure the impedance between this node and AC ground. So the resistance that is obtained thus is a resistance tied between this point and AC ground. So what we see at the collector of Q1 is RC1 to AC ground and 1 over Gm2 to AC ground. So these two are in parallel. So we can say Vx over Vn is equal to minus Gm of this transistor times RC1 in parallel with 1 over Gm2. Okay. How about the voltage gain of the second stage, meaning V out over Vx? V out over Vx, that's from here to here, the gain from here to here. That's a simple common base stage. The base is at AC ground, so the gain is just given by Gm of the transistor times the resistance that we see in the collector, which is RC2. So this one is just Gm2 times RC2. And we multiply these two to find the total gain. So we have AV is equal to minus Gm1 RC1 over 1 over Gm2 times Gm2 times RC2. And we just leave it as shown here. So one point of this exercise is to show you that as we learn more topologies, we have to be quick with their properties so that we can write them without drawing the equivalent circuits again and again. You can see that if you would attempt to draw the equivalent circuit of this topology, well, it would be pretty complicated. You would have to write lots of equations. So we need to know the properties of the common emitter stage very well, the properties of the common base stage very well, and so on. Okay, so that is that little circuit. All right, we are now ready to look at the bias design for a common base stage. So let's go to bias design. The principles are the same as what we did for the common emitter stage. We realized that somehow we need to generate a bias for the base, so we use the resistive divider. Here is the same thing. There's a battery here, so we need a resistive divider there. So lots of little things like that. Nothing really that new, but we just have to make sure that the transistor has, first of all, operates in the forward active region. Second, carries proper collector current. And third, its base is properly biased and all that. Okay. All right, so let's start with the transistor. And what do we do with the base? We need a battery, all right, so we'll just put a resistive divider there. That's not a big deal. Here's our resistive divider, R1, R2. That's great. This goes to VCC, the battery that we have, the supply, power supply. And then we have a resistor from here to here, RC. So we're good to go. Almost. All right, so the question is, do we need any biasing device at the emitter? Well, maybe, maybe not. Let's consider one example, which I showed you just a moment ago. I said that a common base stage might be useful in interfacing with an antenna. So let's go ahead and connect an antenna to the input of the common base stage and see what happens. Again, we are only concerned with the bias conditions, not with the signal. But something strange may happen when we try to connect an antenna. So here, I will connect an antenna here. All right. The question is, will the circuit work? Meaning, will the circuit have proper bias current and everything else? Well, we have to understand what this antenna is like. And for that, I can give you one example. This is called a V antenna. Oh, it looks like a V. And you can see that it consists of two conductors. And we have these 2 points that will be connected to the LNA input and ground. Okay. So is there a problem? By the way, this V can be created in 3 dimensions, in which case we get a horn antenna. This is called a horn antenna. If you look very carefully, you can actually see there's a hole in the middle, which means this is, it doesn't have any connection between the 2 terminals. But anyway, let's just focus on this. We see that these 2 wires are not connected. That's how an antenna is created. We have one wire here, one wire here. If we apply a signal to this, let's say a 2.4 gigahertz signal for Bluetooth, then it radiates. Okay, so now I am at the receiver. So I'm receiving the signal from the air, it comes to the antenna, generates some electrical signal here, and I would like to give it to this common base stage to amplify. I connect one terminal to the emitter, the other terminal to ground. So that's fine. But the question is, if there's no signal, so let's say nobody's transmitting anything, the antenna is not receiving anything. If there's no signal, do we have the proper bias current in this device? Okay, well, let's say that the bias current starts from here, from the battery, goes through RC. I'm looking at positive charge. Goes through RC, comes down the collector, goes through the base, comes down the emitter. Now, where does it go? Well, positive charge has to start from the positive side of the battery and go to the negative side of the battery, right? But can it do that? This antenna is an open circuit as far as a DC current is concerned. You can see that these 2 wires are not connected. So when the current comes down here, it has nowhere to go. It cannot go this way, it cannot go this way. So this device is incapable of carrying a DC current, simply because what we have connected here is really an open circuit as far as DC is concerned. It's not an open circuit as far as a signal is concerned, 1 gigahertz or 5 gigahertz, but as far as DC is concerned, it's an open circuit. So that is the problem. Now, some antennas are like this, some of them are not like this, but we could have that situation. All right, so if indeed this antenna is equivalent to an open circuit, I'll just show it like this. So that antenna doesn't allow us to have a current this way. We have to have some other device that we add ourselves from this emitter to ground to carry the bias current of the transistor. So we should be looking for some sort of 2-terminal device that is capable of carrying DC currents. What 2-terminal devices do we know? So DC current conduction is possible by resistors, current sources, and inductors, as you might remember. In this course, we will try to use a resistor, a current source, but in more advanced courses, we can also try to use an inductor. Okay, so what this says is that in order to make sure that the bias current that starts from here can actually find its way to ground, we need to use one of these three. So let's go ahead and put a resistor here. I'm going to call it RE. So please understand that the sole purpose of RE is to allow the current, the bias current of the transistor to flow to ground. That's it. Otherwise, we prefer not to have anything here. Okay, so should RE be a relatively large resistance or relatively small resistance? Well, let's try to model this antenna by a simple Thevenin circuit, right? We can do that. So here's what we really have. We have a voltage coming from the antenna, which we call V ant, and then we have some sort of resistance R ant, typically 50 ohms, and then we have a resistor here, RE, and then we have the common base stage up here. So what is the effect of RE on the signal itself? All right, so the signal starts from here. You have some current flowing through this resistor. The current arrives here. Now what does it do? Well, some of it goes that way, some of it goes this way. Which one is desirable? It is this current that has to go through the transistor and come out through RC to generate the voltage of interest, V out, right? So the current that goes this way is wasted. All right, so if this current is wasted, let me change the color of my pen so that I can show you this color, this current. So there's a current going this way, there's a current going this way. And the current that's going down through RE is wasted, the signal current. Now, how do I minimize this wasted current? I would like to maximize this resistor. If you remember, when a current splits, it splits according to the impedance that it sees on the other side. So if you're looking for the current that goes this way, if you're looking for the current that goes this way, that current is given by this current times this resistor over the sum of the two resistors. Intuitively, you can see that if this resistor is very large, no current can pass through it, right? So we want to maximize RE. Now when we say very large compared to what? Well, the current that comes in here, so let's call this I ant, the antenna current. This current was split, and we will call this I1, we'll call this I2. Now if you go back to your basic circuit theory and remember how a current splits between two paths, you will see that I1 is equal to, the current that goes this way is given by this impedance, RE, divided by RE plus this impedance. How much is that impedance? That is the input impedance of the common base stage, 1 over GM. So plus 1 over GM times the antenna current. So I1 is the desirable current. We want to maximize it. I2 is the undesirable current. And what this equation tells us is that the best we can do is try to make this 1, so that all of the antenna current ends up being I1. All of the antenna current goes that way. And for that to happen, RE must be much greater than 1 over GM. So that's how we would choose RE. RE has to be large, and specifically much greater than 1 over GM, maybe 10 times. All right, so that the current is not wasted through RE. All of the signal current ends up going through the transistor to the collector through RC and generate a voltage for us. Okay, so that's the principle that we have to follow. And now we have chosen this value So for example, if the bias current is 1 milliamp, 1 over GM is 26 ohms. So we might this to be 10 times that, 260 ohms. That's for this. Then we know how to choose these values, and then we just have to see how RC is chosen to make sure that the collector base junction of this device is not forward biased. So those are conditions surrounding this bias network. Okay, so let me go over an example to hammer these in. So like before, we assume our VCC is 1.5 volts, the power budget is 1.5 milliwatts, beta is 100, and so on. And we know that from the power budget, we get a collector current of approximately 1 milliamp. Let me erase this. 1 milliamp. Okay. So I'm thinking maybe RE should be 10 times 1 over GM. 1 over GM is 26 ohms. So 1 over GM is 26 ohms. So maybe I'll pick RE to be 10 times that, 260 ohms. Okay, how much is the drop across RE? The DC drop, before any signal comes in. Before any signal comes in, just imagine the antenna is not here, right? The antenna, remember, the antenna is an open circuit anyway for DC, right? So imagine the antenna is not here. RE is 260 ohms, and I'm allowing a collector current of 1 milliamp through it. So the voltage from here to here is 260 millivolts. So that says that VE is 260 millivolts. VE meaning the emitter voltage right here with respect to ground. Okay. How about this voltage? How do I choose this? Vx. Well, we write the KVL in our mind. We say Vx from here to here is equal to VBE plus the voltage across RE. The voltage across RE is about 260 millivolts. The base emitter voltage is about 800 millivolts. So Vx is the sum of these two. So we say Vx is equal to VBE plus VE, and that's approximately equal to 1.06 volts. So the resistive divider has to be designed such that with a 1.5 volt supply, it gives us Vx equals 1.06 volts. Now, we also remember that the current flowing through R1 and R2 is chosen approximately 10 times the base current. The base current is 1 milliamp divided by 100, 10 microamps. So this current has to be approximately 100 microamps. So we say VCC over R1 plus R2 is 100 microamps. And because Vx should be 1.06 volts, we say R2 divided by R1 plus R2 times VCC should be 1.06 volts. That's what the voltage divider does. From these two equations, we can find R1 and R2. So that gives us R1 is equal to 10.6 kilo ohms, and R2 is 4.4 kilo ohms. So we have almost everything we need. We calculate these resistors, this resistor. We just have to find RC. Okay. We would like to maximize RC because we know that the gain of the common base stage is proportional to RC. How much can we choose for RC? What's the maximum value? Well, again, if RC is too large, this DC voltage will be too low, the transistor goes into saturation, just like what we saw for the common emitter stage before. So what I will do is I will choose VC, the collector voltage. These are all DC quantities, no signal. Should be equal to, should be greater than or equal to Vx. This voltage should not go below the base to make sure that the transistor does not enter saturation. And we know that Vc is given by VCC minus RCIC. So VCC minus RCIC should be at higher than 1.06 volts. So from there you can find RC, and that comes out to be 440 ohms. So now we have all of the quantities that we're looking for. The circuit is designed according to this supply voltage, power budget, and this condition where we wanted RE to be much greater than 1 over GM, so that when we apply signal here, most of the signal current goes to the transistor, not get wasted. Okay, now if I had been more conservative and to satisfy this, I would have said, no, I want RE to be 20 times 1 over GM. What would have happened? So let me change the color of my pen here, and I'll show you what happens. So imagine that instead of 260 ohms, I choose 520 ohms. For example, right? Then what happens to this voltage? The DC drop here, it doubles. So that becomes 520 ohms. If this is 520 ohms, what happens to Vx? Vx is 800 millivolts above it. So Vx goes to 0.8 plus, sorry, this is 520 millivolts. So 0.8 plus 520, so that's 1.32 volts. So Vx would have to be higher. If Vx is higher, what happens to the collector voltage here? The collector voltage cannot be allowed to be less than Vx. So we have to choose the collector voltage also to be no less than Vx. So this condition still has to hold, which means we have to choose RC so that now this number is 1.32 volts. Now what happens to RC? RC will be lower. I don't know how much it is, but you can calculate it, right? Because if this number goes up, RC has to become smaller so that this number goes up. So because RC is lower, what happens to the gain? The gain will be lower. So AV drops. So that's the price that we pay if we pick RE to be larger and larger to satisfy this constraint. We are losing gain very quickly because RC becomes smaller and smaller. So typically we don't go really much beyond 10 times 1 over GM for these reasons. All right, our time is up. I will see you next time.